So sorry for the AV setup today. Since we're in a different room, it's a little funky. Oh, maybe I can zoom in. Oh, look at that. That'll be better. Not horrible, right? Okay. So sorry, I'm kind of dual docu-camming it. Going for statics lecture in 3D, right? 2 cameras, and then you can get the 3D of my paper. It's pretty exciting to watch 3D notes be taken instead of just 2D. Yeah. Any questions? I haven't got to your graded problems yet. I will have them back for you on Monday so that you can digest for turning in your next graded problem, which is posted, same spot, coursework. And I went looking for a better problem, and I didn't find one. So I stuck with the bulldozer that I had because I liked it. So you have a bulldozer problem for this week. Any questions for me?
What do you mean when you say bulldozer problem?
The problem has a bulldozer in it.
Mm-hmm.
Oh, like an actual bulldozer.
Mm-hmm. Yeah, it's got a bulldozer in it. It's pretty sweet. Not gonna lie.
Don't read into suggestions too hard.
I'll show you. I told you I like making things, right? I did. I'll show you a picture of it. It's a pretty awesome bulldozer too, if I do say so myself. Wait for it. Wait for it. Here it is. Okay, you ready? Here's my bulldozer I made. Kind of hard to see. It's very little. Those are my sons. So he's not using the blade to flatten things, he's using the tracks. That's alright. Oh dude, that kid is a master on that thing. He can back a trailer like it's going out of style, man. Like, so that's why I have a special place in my heart for bulldozers. Okay, so let's talk statics. We were talking all about vectors, right? And I told you we were going to close out our vector talk today. We're actually going to talk about vectors all term, but we're going to stop talking about the math of vectors and start talking about how vectors are used. So this is the last mathy part of vectors, and it's the dot product. Okay. Okay, so the dot product is a way that you can multiply 2 vectors. So we could have A dot B. Okay? And there's 2 ways of defining what A dot B is. One is you multiply the scalar components in the x, y, and z directions and add them together. So that would look like this. AX times BX plus AY times BY plus AZ times BZ. Okay? And that's going to give you, what will that answer be? Will it be a scalar or a vector? It's going to be a scalar, right? Because I'm taking the scalar components in the x direction and multiplying them, and then I'm taking the scalar components in the y direction and multiplying, and the scalar components in the z and multiplying, right? So this will end up with one giant scalar. This is also, it turns out, equal to, if I took the magnitude of A and the magnitude of B, and I multiplied it by the cosine of the angle between them. Okay. So why do we really care about this? It's a good question. I regularly asked in most of my classes, like, so what? So why do I care, right? I care because, say, for instance, we are given yesterday my son was driving his go-kart. It's been kind of a process. It was given to us and it didn't really work, and so we fixed it. And it turns out that when we fixed the carburetor, a little screw fell into the carburetor that caused the gas to stay on. Unfortunately, it has a kill switch, but he turned it off while he was driving it because the gas was like stuck on. So he's just like flying across the field. So he turns it off. He's 8, and this was a good choice. And then he got out and he flipped the kill switch back on and decided to restart it. Well, when he did that, it started and it just took off without a driver, right? And he couldn't stop it. And so he came inside and he said, "Oh, Dad." And it turns out that it drove right into a barbed wire fence, which barbed wire fences are stronger than you might guess. Strong enough to stop a go-kart, fortunately, right? Because the barbed wire fence is right against the road, so nobody likes a runaway go-kart. But what happened is that his go-kart has like a little, well, I'll draw you a picture of the go-kart. It's a Yerf dog. Any of you familiar with go-karts? So it looks kind of like this. It has a seat that he sits in. And this is like the roll cage, right? Well, when it hit the barbed wire fence right here, this got bent. Like that. Okay? So now the roll cage is bent right there. And the way that happened, if we looked at just that pipe or beam, if you will, right? Here's the piece of his roll cage. And the barbed wire exerted a force on the roll cage. Does that make sense? So it pushed really hard and it caused it to bend. And maybe we want to know, well, how much of this force is in the direction of this guy? Well, we could get a protractor out, right? But that'd be tough. We'd have to like figure out, okay, it's perpendicular to here, and that'd be hard to measure, okay? It might be a lot easier to say, okay, I know the direction of this vector, and I know the direction of that vector, and I can figure it out. But the problem is, if we look at it from above, here's the barbed wire fence. The go-kart hit the barbed wire fence at an angle, right? So this was the go-kart driving, and it hit it at an angle. Everybody all right with that? Because if we just had this two-dimensional problem, you'd say, well, if you know it's perpendicular, you can just figure out what that angle theta is, right? But now what happens? Now we've got some really funky junk stuff going on, right? Because we have this angle, we have this horizontal, and then we have the roll bar that's going at an angle, okay? So all of that gets really tricky. So an easier thing to do would be to maybe set an origin right here and figure out, okay, what's this vector? What's that vector? And then I can use the dot product to help me solve where the component of this that lies in this direction. I'm getting lots of confused looks. Apparently you guys don't appreciate go-karts as much as you should, so I'm going to move on to a different example. Okay? Let's say, fine, I'll just use a lame, boring one that's supposedly instructive from the book. How about that? Like that better? Okay.
Are you supposed to record your lecture?
I am, yeah. Is that okay? Did I just say something that I'm going to be embarrassed about? If I'm like become a Supreme Court justice or something?
Just look it out.
All right. So I'm going to go ahead and, oh shoot, let me freeze. Oh, I'm not going to be able to, well, maybe I can double freeze. Freeze. Oh, yeah, look at this. I'm going to double up on my freezing skills. And freeze. My computer will ever, there we go. Okay. So we've got this window. It's held open by a chain AB. Determine the length of the chain and express the 50-pound force acting at A along the chain as a Cartesian vector and determine its coordinate direction angles. Yeah, that's kind of lame. I'm going to change the problem, okay? But we'll use this drawing. Everyone see it? I'm looking at 210 here. 110. Okay? So go ahead and put that in your notes, and then we'll talk about it. So it's going to take you a second to draw that, hopefully. No. Mm-mm. No way. Mm-mm. Okay. So this is the drawing I come up with. It's beautiful, isn't it?
Yes.
Okay. So, and I'm changing the problem, you'll note, it says given this door or window, this hatch that's opened in these dimensions, find the components of f in the x, y, and z, and projection of f onto AC. So the first half of the problem is stuff we did on Wednesday, right? We need to find the position vector, which would be the position vector a to b, and then we can multiply that, or find the unit vector and then multiply it by 50 and we'll get the components in the x, y, and z, right? Okay, so how are we going to find where A is? Well, we know the coordinates of A. We don't know what it is in x. Well, sure we do. We know that it's 5 cosine 40, right, in the x direction. And that it's 8 in the y direction, and that it's 5 sine 40 in the z direction. I can try. How's that? Anyone have a 5 cosine 40 and 5 sine 40 for me?
5 cosine 40 is 5 or 323. And 3.21.
Okay. Everybody okay with those coordinates? So how do I find the position vector now? I'm looking for the position vector R, B, A, right? I'm looking, no, sorry, A, B. R, A to B. Anybody remember from Wednesday?
A minus B.
B minus A. Square the x, y, and z, and then square the total. That's for you.
That's good. That has more to do with magnitudes. I heard somebody else had it though.
B minus A.
B minus A, right? So I'm going to take the coordinates of B. Maybe we should throw the coordinates of B on here. It looks like they're 0, 5, 12, right? It's 0 in the x, 5 in the y, 12 in the z. So RAB is going to be the endpoint 0 minus 3.83. So negative 3.83 I hat. 5 minus 8, negative 3 j hat. And 3.21, excuse me, no, 12 minus 3.21, which is 8.79, I believe. So plus 8.79 K. Right? Okay, so what's the magnitude of that?
10.04.
And how'd you find that?
Square all the vectors,
Mm-hmm.
unit vectors, and then square root it all.
Yeah, so not unit vectors, the components. Square the magnitude of the components. That's okay. So square the components and take the square root, and you came up with 10 point something?
10.04.
All right. What are we doing? Why are we doing this? Anyone know? To get a unit vector, right? Why is a unit vector important, Jake?
So you can multiply it by the force to get a vector that's going to the force.
Exactly. So we're taking the position vector to find the unit vector so that we can multiply it by the magnitude of the force that we know acts along that line, and that'll give us the components of the force in the x, y, and z direction. Right? Everyone feel good about where we're going? I feel like sometimes we get in these problems and we get like, okay, we're doing dot product, why? Right? Okay. So here we are. So our unit vector, now that we have the magnitude, to find the unit vector of A to B, I'm just going to take RAB and divide it by its magnitude. So I'm going to have, I'm just going to round it to 10 as the magnitude, right? It seems darn close to 10 to me, 10.04, and that's going to make me so I can do with the division in my head, okay? So I'm going to say the unit vector is negative 0.383 I hat minus 0.3 j hat plus 0.879 k hat. Right? So I'm just dividing this by 10, each of the individual pieces by 10. Everybody happy with that? Okay. So if we've got that, then let's now multiply by our force vector of 50. So now we take F times UAB, right? And F is a scalar multiplying a vector, right? So what does the unit vector, what information does a unit vector always contain? Direction. And it has a magnitude of 1. So when I multiply this unit vector of magnitude 1 times F, it's just going to distribute that 50 pounds in each of the directions that it needs to go, okay, so that it would, each of those orthogonal vectors then would add up to 50 pounds in that direction. Okay, so 50 times 0.383? Negative 19 I hat. 0.3 times 50, negative 15 j hat plus 46, 44 k hat. All right. So now we know the components of F in the x, y, and z. This would be F sub x, F sub y, and F sub z. Okay. That's what we did on Wednesday. Now what I'm going to say is I want us to find the projection of the force vector F onto AC, which I'm defining as this line that goes from A down to C. Can anyone look at that and tell me what the angle between RAB and RAC is? The answer is no, you can't. Okay, right? You can't look at that. I mean, we could guess. We know it's greater than 90, right? It's less than 180. So there's only an infinite number of possibilities between there, right? Okay, so we don't know. So how do we do this? Well, this is where the dot product comes in handy. Okay? Because I can take the dot product, if I figure out, let's figure out what AC is, what the RAC. Okay? So I'm going to need some more paper, I think. No. Oh boy. This is a treat. 2 DocuCams at once. Oh boy. What have I done? Okay, so let's figure out RAC. So the vector RAC is going to start at A and go to C. So we know we've figured out the coordinates of A, right? 0.3838 and 3.21. So I'm just going to put these on this page too. 3.83, 8, and 3.21. And the coordinate of C, anyone see what the coordinate of C is? 0, 8, 0, right? So RAC, that's A going to C, is going to be negative 3.83 in the I hat direction, plus 0 in the J hat direction, no change in Y, negative 3.21 in the K hat direction. Right? Because we're talking about the vector that goes like this. All right? So what I'm trying to find, just to be clear, is this angle right here. Okay? Just trying to find the angle between the vector RAB and the vector RAC. Maybe I'm going to change this. Instead of saying the projection of F, I'm just going to say of AB onto the RAC. Okay? So here's RAC. We had RAB up here is negative 3.83I minus 3J plus 8.79K. All right? And we're looking to find, and then we had UAB as well. UAB we said was 0.383I negative minus 0.3J plus 0.879K. So if we want to find the projection of RAC onto UAB, we just do RAC dotted with UAB. Oops, can't see what I wrote. Sorry about that.
Why are we using UAB?
Why are we using the unit vector?
Yeah.
Because it won't change the magnitude. Right? If we use the full vector, it multiply. If you use the full vector, it doesn't give you the amount of AC that lies along UAB, because your UAB, how can I explain that? Let's do it this way, and then we'll do it using RAB, and you'll see that it changes it by its magnitude. Okay? So RAC.UAB, we said, is going to take, I take negative 3.83, and I multiply that by the same here, negative 0.383, plus 0 times negative 0.3, plus negative 3.21 times 0.879. Okay? And these are all scalars. So this one we can see is 0. Can someone add these up and tell me what the sum is? Excuse me?
I got negative 1.35.
Negative 1.35.
So I could have messed it up.
Okay.
I got that too.
All right. So what this is telling us is that negative 1.35 of is the length of the vector projection of AB onto AC. So if we were to see how much comes down at a perpendicular right angle onto this vector, the magnitude of that little guy right here, oh gosh, this is a terrible drawing, but if I tried to, yep, 1.35 is when it lands on this, okay? The shadow of it, if you will, at a 90-degree angle is going to be 1.35. Super not satisfying. I liked my go-kart example better, but y'all were hating on it, so. Okay, now Brendan had a good question. Why are we using the unit vector versus the full vector? So if we use the full vector, so I did RAC dot RAB, which you can do, it's just going to give you something else. Now I'll have 3.83 negative times negative 3.83 plus 0 times 3 plus negative 3.21 times 8.79, and this gives you a much larger answer. Okay, so like if we do that, that's going to be 14-ish plus 26-ish, so that's going to be around 40. What's the answer if you do these? Because that one's positive, right? Okay. Negative 13.5, right? Which the difference here is a factor of 10, which is the magnitude of what? This guy, right? So it's saying it's 10 times the length onto that guy.
Okay, so I have another question.
Okay.
So you said the projection of what, of AC onto AB, no, AB onto AC, right?
Yep.
But if the angle is obtuse between them, I'm having a hard time imagining how that's such a small number.
Great question. I drew this in the wrong spot. It should be, it's negative, so it's telling me it's in the opposite direction of that guy.
Okay.
Right?
I see that.
So if we rotate it around, what we have, I'll try and draw it. You're gonna.
2D.
You want me to draw it in 2D?
Yeah.
Right. So the edge of the door. Let me try to see if I can do this. Not convinced that I can, but I'm going to try. Maybe if we look at it, let's imagine we're looking from here. We're looking down the y-axis. Okay? You all right with that? So we're going to look down the y-axis, and we'll see the edge of the door going at a 40-degree angle, right? That's 40 degrees. And then we're going to see that it goes up to this point up here, right? The 12 feet up. Does everyone see that? So then this is RAC. So then if I'm projecting this guy onto this vector, So let me put my labels on here. Here's A, here's B, and here's C. So now when I project RAB onto RAC, I end up with negative 1.35.
Is that what we're doing? Is 215?
Bend one to my will. All right, so we're asked to find the angle between these two cables, and then we're gonna do both of these actually. Determine the magnitude of the projection of the force F1 along the cable AC. So we'll do both problems, 114 and 115, because this will be your guide for doing your homework. All right? So you can follow this, I hope. It's like famous last words. Okay? So let me draw this and get it in my notes, okay? Okay. Looks like A is right here. C is right here. And B is right there. Right, where this is 2, 3, 3, and 2, 3, 4. So A has coordinates 2, 3, 3, and this is negative, right, in the y, so 2, negative 3, 3. B has coordinates 0, 3, 0, and C has coordinates, what would that be? Negative 2, 3, 4. Everyone good with that?
Yep.
Okay, and we're given, we have one vector like this, we have one, oh shoot, missed it, but one vector like that, and this guy has a magnitude of 70 newtons, then this one has a magnitude of 40 newtons. This is F2 and F1. Okay? So, the position vector, let's start with that. Let's go RAC. Okay? So that's going to be C minus A. So negative 2 minus 2 is going to be negative 4. 3 minus negative 3 is going to be 6. 4 minus 3 is going to be 1. Everybody agree with me on the position vector AC?
Yes. A should be at 3, negative 2, 3. Right? Because the x-axis is coming out towards us.
Yep, the x-axis is coming out towards us, so it's 2, x, y, z. So along the x-axis is 2, I think, right?
Yeah. Oh, I got you now.
Okay. Then let's do RAB. Okay. RAB, that's going to be A going to B, so I'll take the coordinates of B and subtract the coordinates of A. So I'll have 0 minus 2. Right? So negative 2 I hat. I'll have 3 minus negative 3 plus 6 j hat. And then I'll have 0 minus 3 minus 3 k hat. Okay, those are my two vectors, position vectors. Now I'm asked to find the angle between them. Let's find the magnitudes of each of them first, okay? We know we're going to need that. So 4 squared plus 6 squared plus 1 squared.
Root 53.
Root 53. here's what we know about the dot product. A dot B is equal to A B cosine theta. And that's what we're going to use to solve this guy. Okay, because we're asked to find this angle between them, theta. Easiest way to do that is to take the dot product using their full magnitudes, right? Then multiply their magnitudes times cosine theta, and we'll end up with it, all right? So let's do that. So A dot B, excuse me, not A dot B, RAC dot RAB. Okay, that'll be -4 times -2. Right, so -4 times -2 plus 6 times 6 plus 1 times -3. Okay, so this is equal to -4 times -2 is 8 plus 36 gives me 44 minus 3, I get 41. Okay, so I'm going to say this is equal to 41. Everyone all right with that? So then I can substitute that back into this guy, and I'm going to say 41 is equal to the magnitude of AC, root 53, times 7 times cosine theta. So 41 divided by root 53 times 7 inverse cosine equals theta. Natasha, you're like, again, why do we need that angle, right? And I agree.
That angle I get.
Okay.
It's just like, for me it was hard to get in a real world, what do you use it for?
Yep.
Like,
Mm-hmm.
36.4.
36.4. Anybody else get 36.4?
Yeah.
Okay. All right. Now, the next part of the problem is more what we were doing last time, and I think this is more real world for the engineer, is we're going to say how much of F, does the problem say F1 or F2? Determine the magnitude of the projection of force F1 along cable AC. So it's saying how much of this 70 Newton force could be projected along FAC. Okay, so how much of this guy ends up pulling in the direction of AC? Okay, and that's where we're going to need to use a unit vector. Which one of those will we need to use a unit vector for?
F2.
F2, right? Because that's the direction along which we're trying to project it. Okay, but can we just take, we're actually going to have to find both unit vectors, right? Why?
Because last time I didn't.
Because last time I didn't and it screwed me up? No? Why? I mean, true, but why do we need to find both unit vectors? Because I'm only going to use one in my final analysis, right?
We looked at that A times B equals B times A, or A dot B equals B dot A. And if you make one of those a unit vector, you have to make both of them a unit vector, right?
No. Okay, so what we're after, right, is we want to do F1 dot UAC, right? This is what the book is asking us to do. It's saying, what's the projection of F1 onto the line AC? Okay, so the line AC, we're just going to figure out what its direction is, but we need to dot it with F1. But how do we find F1? We need to find the unit vector of AB and multiply it by 70, right? Multiply it by the magnitude of that force, okay? So we can find both these unit vectors pretty quickly. UAC is going to be negative 4 over root 53 I hat plus 6 over root 53 j hat plus 1 over root 53 k hat. UAB is going to be negative 2/7 I hat plus 6/7 j hat minus 3/7 k hat. Wouldn't you know it, it's neat that we're multiplying that by 70 pounds.
Wow.
Tricky, tricky. This is what happens when a book gets to make up the problem instead of your instructor doing it on the fly, right? Because what I'm interested in finding is F1, which lies along the line UAB. So I multiply my unit vector. I'm going to multiply this by the magnitude of 70 pounds, right? And I'm going to say that F1 is equal to negative 20I plus 60J minus 30K. All right. So the component of F1 that lies along that UAC, now I dot product it with the unit vector. Okay, so now I can take F1 dot UAC. So UAC we figured is right here. So let's make it bigger. F1 dot UAC will give me negative 20 times negative 4 over root 53 plus 60 times 6 over root 53 plus negative 30 times 1 over root 53. And that's just the scalar. Better? Nate?
Why do we multiply the unit vector of AB times 70 pounds?
Because that's the force.
Yeah, because if we go back to the problem here, right, we're told that F1 has a magnitude of 70. So the question was, why do we multiply the unit vector of AB times 70? Why was I doing this step? Because we're told that there's a force of 70 newtons that lies along this line AB.
Okay.
So the actual force vector, when we say there's a force of 70 newtons, that's a scalar.
Right.
It doesn't contain direction. And then we say it lies along AB, I need to give it the direction of AB, which is the unit vector.
Okay.
Right? So I take 70 pounds and I multiply it by 1, but 1 giving us the direction.
Okay.
Okay?
Gotcha.
All right? So did anyone come up with what this is equal to? 56.3? Sounds like 56.3 pounds. Newtons. I just converted it just for fun in my head, like, you know. Okay, so 56.3 newtons of this 70 newtons acts along C. So if I wanted to determine how much force a member along here could carry, like maybe I know I'm pulling along AB and I know I can place a support at AC and I want to know how much load that support will take, it's going to be 50 pounds. Will it be in static equilibrium if that's the only support? No, right? Because 50 pounds and 70 pounds, they don't add up at all, right? So it wouldn't be in static equilibrium. We'd have to add another one. Where would the most efficient place be to add another one? I don't expect you to know this, but it'll be an interesting intuition question. Opposite? What do you think? If we're going to say we are going to counteract this 70 Newton force by placing one support along AC, and that's a given, so you have one support here and you have the force here, where should you put the other one that would be most efficient?
Perpendicular to both of them.
Not to both of them. Not to AB. To AC. Okay? So the next most efficient, because we're saying 50 pounds along here, and then if I had one there counteracting in that direction, that would be the most efficient way to do that. Okay? That'd minimize the load. All right? Totally not super important that you get that, but that is kind of the function of knowing the dot product, is we say, okay, how much is projected onto here? And then the rest of it, we know, is perpendicular. Everything that's projected onto here is just the shadow of it in that direction. So then if I took the shadow going perpendicular to that, right, that'd give me the other component. Okay? Natasha was right that the most efficient way to counteract this would be just to put one right behind it, right? You just have 70 newtons pulling in the opposite direction, and that'd be best. But lots of times we can't do that. We have to do something off axis. Okay? Yeah, so like I said, you know, on Wednesday, we'd spend the first 20 minutes going over dot products. Sorry about that. It was an hour.
Because we didn't do the go-kart.
It's because you didn't like my go-kart.
I was fine with it.
Uh-huh.
Driving the go-kart.
Yeah, driving the go-kart's fun too. Okay. So what? So we have 20 minutes left. We're going to talk about free body diagrams, which I think it must have been recording the whole time because it shows that I've talked for an hour. So that's going to be interesting. Okay. Chapter 3 is when we really start saying, okay, let's be engineers, right? So far we've just been doing the maths. And the maths are fine, but you can see they're not my, like, strongest piece. They're not the thing I have to add to you the most here, right? So I can blunder that. Hopefully I don't blunder as much in the engineering side of it. So what we're going to be looking at is the equilibrium of a particle, okay, in the next couple chapters. Anybody remember what we said about a particle? What's important that we remember about a particle? It's a point, okay? It's a point in space. So what does that mean?
There's no surface area.
Okay, no surface area, or another way to say that is no size. Is that okay?
Yeah.
Okay, but what does it have? Mass. Okay, mass but no size. So what we talked about is maybe we'd have a Volkswagen Bug. Okay. It's not a go-kart, it's a Volkswagen Bug, dude.
Sure.
Okay. See what is a Volkswagen Bug more like? Yeah, there we go.
There's Volkswagen Bug.
Yeah. So we've got a Volkswagen Bug, and it's sitting on the ground, or it's, you know, driving down the road, and it runs into a pole. It's a bad idea in a Volkswagen Bug, by the way. There's nothing there between you and the pole. Okay. So, well, an old one. New ones are better. But. So you're driving down the road, and we want to talk about the forces that are happening here. When we treat this as a particle, we say that all of the forces act at its center of mass, okay? And rather than having to be an amazing artist like I am, like I realize that's just, I don't want to intimidate you guys with my skills of drawing, and I don't want you to feel bad about them, okay? I don't want you to feel bad about yourself. So what we're going to do is we're going to draw free body diagrams, which involve doing things like this. If I'm going to draw this as a free body diagram, I'm going to go like that, okay? You can draw a car if you want, but we can also, when we're dealing with a particle, a dot works, because size doesn't matter. Then what we need to do is what we're trying to say is, look, I'm looking at the forces that are acting on the particle. That's what I care about, okay? And I want to quantify all of them. So let's pull the Volkswagen out of where it's at, and every place that it's touching something, it's likely that there's a force there, okay? So where's the Volkswagen touching something? The ground, okay? And what type of force would the ground exert on Volkswagen? Okay, I heard friction. What else? A normal force, right? So hopefully the ground is holding this guy up, and we're just going to put an arrow on that and say it's normal. Okay, Paul says maybe the force of friction. Maybe before you hit the pole, you slam on the brakes. Okay? So which way would the ground be acting on the car if you slammed on the brakes? Left or right?
Which way is the car going?
It's going towards the pole.
Right.
Are the wheels still turning?
Doesn't matter. It's smashing into it. The force of friction is pushing the car back, right? So the ground is pushing back on the car. Now the car is pushing the ground forward, equal and opposite, but we're going to say that the force of friction is pushing back, okay? And I usually do a capital F with a subscript F for the force of friction. What other forces are acting on this car? Let's say it has contacted the pole. Yeah.
The pole force.
The normal of the pole, which I'm going to do N sub P. Does the car experience any forces that aren't due to touching? Gravity. And we could say mg or w or whatever you want. And it's fine if you draw it up or down, right? So we could draw the exact same one, right? Same situation. I could have drawn like this. Right? I could have done that. It's the same thing. They're just sliding vectors. So it really doesn't matter where I put them on the particle, whether they're going up or going down, but as long as their direction is correct, we're fine. Okay? Any other forces acting on this guy? So momentum's not a force, but it has momentum. Yep.
Air drag.
Okay, maybe we'd have air drag. Typically in this class we're going to say, nah, doesn't matter. Okay, no drag. But yeah, you could say that there's like F sub D, force of drag. Sorry. So the things that are important in drawing a good free body diagram, I think it's fun to draw whatever it is you're working on, and once we get to rigid bodies, you're going to have to draw what you're working on. Okay? So you can either draw it as a particle or draw it as the actual thing, but just draw it removed from its surroundings, right? So we're going to come to, here, let's just look at some of the problems we're going to have, and we could draw free body diagrams of them, okay? So let's look at, oh, yeah, these are going to be so fun. Okay, so let's look at this 321. I'm going to want to draw a free body diagram at point A. Okay? So, like 320 says, a vertical force P equals 10 pounds is applied to the ends of the 2-foot cord AB and spring AC. If the spring has an unstretched length of 2 feet, determine the angle theta for equilibrium. Take K equals 15 pounds. All right, we'll get to some of that. But let's just say I want you to draw me a free body diagram of point A, because that's where all the action's happening. Okay? So anytime we have a rope, we draw a tension force. So what we would say here, I'm going to draw my free body diagram. That's point A. And I'm going to denote this as T sub B, right? Because it's going in the direction of point B. Okay. Then I'm going to have T sub C and 10 pounds down. Okay, that would be my free body diagram. Now, since we're drawing vectors, here we don't know. We know 10 pounds, and we know that it's straight down. In this book, if something looks straight horizontal or straight vertical, assume that it is. Okay? So we're just going to make that assumption. If it looks straight down, it is straight down. Next, we don't know, we're asked to find this angle theta. So what we're saying is we don't know where TB is, right? And we actually don't know where TC is either. These are just two vectors that are off in space, okay? We'll talk about how to solve this later, but when you draw a free body diagram, what you want to do is choose your point and then put in all the places where there are forces. So there are three things you need to be cognizant of, three different types of special cases that I want to make sure you're familiar with, okay, as we solve these. One is springs, okay? So springs are characterized as having a spring constant K. And K has units of force per length, right? So that's pounds per inch or newtons per meter, okay? And so typically springs are used such that the force is equal to Ks. Or sometimes we write this K delta S, or sometimes K S final minus S initial, right? However you want to do that, okay? So what this is saying is that if I have a spring with a K value of 10 pounds per inch, okay? And then I'll say it has an unstretched length. So this is where there's no load on it. Unstretched length of, let's say, 6 inches. Okay, so here's my spring. Right? And when it's just sitting here and static, you know, nothing pulling on it. Yeah, sorry. Okay. When my spring is just sitting there with nothing pulling on it, it has a length of 6 inches. Okay, that's the unstretched length. If I then pull on the spring such that it elongates, so now I'm going to, a moment later, pull on it, stretch it out a little bit, right? And now it has a length of 8 inches. To hold it in that position, I can figure out what the force required to do that is by using this formula, FKS. So the force will be the spring constant, 10 pounds per inch, times S, which is the change in length, which in this case is 2. And I can just look at it and say it's 2, or I can say that it's 8 minus 6 is 2. That'd be fine. Whatever. It's 2 inches. So then 2 inches and inches cancel, and I end up with, it takes 20 pounds. Okay? So springs always have a force, a spring constant, that you multiply by the amount you've distorted them, and that will tell you the load, or the force required to do that. Works the same with compression springs, right? Maybe I have, oh, my favorite playground ride.
Merry-go-round.
Playground?
No, ooh, I've got a good story about the merry-go-round from this summer, though. You know the little thing that looks like a goofy little horse with the saddle? They used to have them at Burger King when they had the Hamburglar jails. Anybody remember those?
Yes.
Oh, yeah.
Hamburglar jails? Where you'd go up the tower and then it was a hamburger. They were awesome. But they had these too, and they have a little saddle, and they're made out of a car coil spring. And you sit on this thing and you rock back and forth like this. So fun. Awesome. Okay, even more fun now that I've got more mass, because I can really get that thing going. Okay, so this is a compression spring though, right? And even in your car, right? If you guys are into cars, and you can change the rate of your spring. So if you, it's actually something that you can fairly easily measure too. If you take your car and you jack it up so that the spring is just hanging there with no load on it, and measure it, okay? And then you put your car down and measure it again, and you know how much weight is on that, you can figure out what the spring constant is, or how stiff your spring is, because it's just a pounds per inch sort of thing. Okay? So this would be, maybe it starts with an unstretched length of 12 inches, and then I put my car back on the ground and it shrinks down to be, let's say 9 inches. And I know that there's a load of 1,000 pounds on that spring, right? So now I know the force F equals KS. The force is 1,000 pounds. Force is 1,000 pounds. That's equal to my spring constant that I don't know times the deformation, which is 3 inches. And I can figure out that K is equal to 333 pounds per inch. Okay, that's the stiffness of that spring, which is actually, it's a fairly common coil spring stiffness in a truck, around 300 pounds per inch. Okay? So those are springs. You're going to need to know how to deal with those. Know that the force is always directed along the line of the spring, right? So if you know the direction of the spring, you know the direction of the force. All right?
That 1,000 pounds, just like the weight of the car? Or
The weight, it's not just the weight of the car, it'd be the weight of the car that's on that spring.
okay.
Because typically you'd have 4 in the car, so this would be a 4,000 pound car.
Okay. All right.
Okay.
Gotcha.
Pulleys and cables. How are we doing on time? Oh, about 4 minutes. Okay. So pulleys in this class look like that. Oops. This is dual thingy. This is for the birds. We're not doing this again. Okay. So there's your pulley. We might put a rope around it like this. Okay. In our class, the pulleys are weightless. They're magic pulleys. They have no weight, no inertia. Okay. And they have no friction. And why this is important, because if I put a weight over here of 10 pounds, that means in order for this to be in equilibrium, I have to pull down here with 10 pounds. Okay? So the tension in the rope is the same everywhere in the rope. All right? That's a big deal. The tension in the rope is the same everywhere in the rope in this class. No matter where you cut it, 10 pounds. Okay? All right. We did not get near as far as I had hoped. I'd like you to read through the rest of chapter 3. There's only 2 sections after this, actually. So 3.3 and 3.4. And they, what we're going to be talking about is static equilibrium. So how do we get that Volkswagen so that it stays in equilibrium? The sum of the forces equals 0. Okay, so that's what we're going to be doing next week. Apologies for trying to bend a problem to my will and failing. That wasn't fun for anybody, but we'll keep going from there. All right? Questions?
Graded problem due next Wednesday?
There is a graded problem due next Wednesday, and it is posted. Okay?